So, are you able to see my screen? Can this one be not? Okay. Yeah. Hi. Are you able to see my screen, Abdul? Okay. Good. Okay. Good. Hi. So I've begun the recording. Okay. Hi. So yeah, I've begun the recording. So I'll just give a quick introduction once again. My name is Bhavya. Okay. I'm a PhD scholar from IITM. I'll be conducting these problem solving sessions for the TOC course, Theory of Computation course, on Tuesdays, 6 p.m. Okay, 6 p.m. to 8 a.m. 8 p.m. Right. So let's begin without any further ado. So all the problems until now, all the weeks until now, weeks 1 and 2, we focused on a particular type of language which are called regular languages. Right. And what are regular languages? Regular languages are those languages which can be recognized by DFAs. Alright. And now what we ask is, okay, I mean, there are so many languages, right? Because what is a language? A language is nothing but a set of strings. So how many languages are there? There can be infinite languages. So are all languages regular? That is something we ask. Or are there languages which are not regular? Or are there languages which are more powerful than regular in other sense? Well, to answer that question, we are looking at this particular topic about non-regular languages, and we answer the question as yes, there are languages which are non-regular. There are languages which cannot be recognized by any DFAs, or in other words, these languages are more difficult to recognize. Okay, so DFAs, as you can see, is a kind of a computer which has very limited memory, right? So using DFAs, it is not enough. We cannot recognize enough languages. Okay, using DFAs, we cannot recognize all languages using DFAs. And such languages which cannot be recognized by DFAs are what are called non-regular. They cannot be recognized by DFAs. So okay, so this session will be application-based session. I will not focus on proofs, okay, because proofs are already done in the lecture videos recordings. So firstly, let's look at pumping lemma for regular languages and its applications. Okay. So what is pumping lemma? Pumping lemma is an attempt to characterize regular languages. In other words, it says that if L is a regular language, then it has some properties. Okay. So let's see what those properties are. So let L be a regular language, then there will always exist a number P, okay, which is also called the pumping length. There will always exist a number P such that if I have a string S, okay, and the length of the string is at least P. I have a string S and the length of the language is, the length of the string is at least P, then S may be divided into substrings, okay, X, Y, Z. So S can be written as X followed by Y followed by Z, okay, satisfying these particular properties. So the first property is, what I can do is, if I power the middle part, the Y part, okay, X to the power I means Y items, or in other words, X, Y, Z, X, Y, Y, Z. This is when I is 2. this is I is 1, and x, y, 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 z, this is when I is 3, right? All, and no matter how many times, this process is called pumping. Okay, you are pumping y into the string. No matter how many times you pump y into the string, the resulting string will always belong to the same language. Okay, here it should be to the same language L. Okay, no matter how many times you pump y, it will always be in the language L. Next, the length of y must not be 0. It should be strictly greater than 0. In other words, what is the only string that has length 0? That is, y can never be the empty string. Okay. Next, the length of xy, the length of this part, okay, should be at most p. It cannot be more than p. All of these three conditions are very important. We'll see soon why it is important. But I hope I recalled enough about what the statement is. Okay, this is the statement. Okay, it might look very huge and menacing, but don't worry. What we want to do is we want to apply it. Okay. And what is an application of pumping lemma? To identify non-regular languages. Okay. Yeah. And how do we do that? Okay. So the idea is as follows. So the theorem says that, okay, L is regular, then it will satisfy these properties. Okay. What we'll do is, we are given a language L, we will assume L is regular. We'll assume that L is regular. Okay. Now, since L is regular, we have assumed, then conditions, okay, not conditions, conditions 1, 2, 3 must always be true, right? Because if L is regular, then these three conditions must be true by the theorem, by pumping lemma, right, by the lemma. But obtain contradiction. What I mean by obtain contradiction, I mean to say that show that this is not true for all xyz. Show an xyz where if I pump y, okay, if I pump y, it will no more be in the language L. It says no matter how many times I pump y, it should be in the language, right? What I'll do is I will pump y, okay, maybe I may pump it several times, but I'll show that, okay, if I pump it a certain number of times, it cannot be in L. This resulting thing cannot be in L. But then this is a contradiction to the lemma, right? So where was the mistake? The mistake was in assuming that L is regular. So we'll say that, oh, okay, then therefore L is not regular. Okay, is this clear? This is how we apply it. Okay, I mean, even if this is not clear, okay, I'll show the example. And then it'll be very clear to you. But the idea is as follows: you just assume that L is regular, then the three conditions of pumping lemma should be satisfied. If I show that for a certain string pumping lemma is not satisfied, then it only means that L is not regular in the first place. L was not regular at all. Okay. So here's the question. So the question says, using pumping lemma, okay, show that the following language is non-regular. Okay, and the language is L equals A to the n, B to the n, C to the n is greater than or equal to 0. So this is the language given to us. We want to show that this is not regular. So how do we go about it? Okay, so the step one is always assume L is regular. Okay, we've assumed L is regular. Now what? Now by pumping lemma, what do you have? By pumping lemma, um, any string, right? Any string S can be partitioned into x, y, z. Okay, S equals x, y, z, such that conditions 1, 2, 3 are satisfied. Okay, now what are the conditions? Okay, so what is the first condition? Okay, for all I, no matter how many times I pump, it should be in for all I. Okay, and x, y, z, remember that y, okay, x, y, z, okay, or in other words, S should be at least of length p. Okay, and by pumping lemma there exists a number p such that, okay, S should be at least of length p. Now for all I, okay, no matter how many times I pump y into the string, it will always be in the language. This is the first condition. Next condition is y cannot be empty. Y cannot be empty. And final condition is that the length of xy should be at least p. Now let's try. Okay. So therefore take any string s. Okay, any string s in the language. Now s will be of the form a to the n, b to the n, c to the n. Okay, because it's in the language, because s is in the language, right? But since we have that the length of the string is at least p, so a to the n, b to the n, c to the n, the length of s is at least p, right? So for ease, okay, let's say a to the s equals a to the p, b to the p, c to the p. Not a to the n, b to the n. We are not working with arbitrary n. Okay, let's say a to the b, b to the p, c to the p. Then we definitely have this condition, right? Then we definitely, then, okay, length of s is at least p, definitely, because what is the length? In fact, what is the length? Length of s is 3p. So we are good with the first. Okay, now let's see. So let's say p is the pumping, and let p be the p given by lemma. Okay, p is the p given by lemma. Now what do we do? Observe the fact that, okay, then of course s can be partitioned. S equals x, y, z by lemma, by the lemma, right? But observe that by condition 3, the length of xy is at least p. Oh no, okay, I made a mistake here. Is at most p. The length of, by condition 3, the length of xy part is at most p. So look at A, and B, and so on, B, C, and so on. This has length p, this has length p, this has length p. And where will xy lie? Since xy is of length at most p, it will lie somewhere here, right? It cannot be more than this, because the length of xy is only p at the max. So xy will lie somewhere here, which means, and always remember to observe what y is, okay, which means that y is consisting only of a's. Since y only lies in this region, it's true for x also, but y consists of only a's. Y is only consisting of a's. Okay, now let's say that let's say that y equals a to the k for some k. Okay, let's say y is some a to the k. Now what we'll do, we will start the pumping. We'll begin the pumping. How will we do it? So S is in L, that is true, right? So let's look at X, Y, followed by Y, then Z. We have pumped one Y to it. What happens? XY is nothing but A to the X, okay. Now look at this. This part is all A's. Now I'm adding an additional A to the K to it. So how many A's are there in total now? Since I've pumped the Y again. A to the, since it contained P A's in the beginning, then I added K more A's because I'm pumping Y in it, plus K, and then followed by B to the P, C to the P. So this is not of the form A to the N, B to the N, C to the N. It is not of that form because obviously K is non-zero, okay, and therefore this is not in L. Since it is not in L, it is contradicting pumping lemma. And since it's contradicting, it means our assumption was wrong and L is not regular. So this is the technique how you do it. Okay. I mean, it could be shortened, the arguments could be shortened, but I wanted to make it very precise what we are talking about. So is this clear? If you have any questions, please let me know right now. Any questions, Suresh?
No, sir. Thank you.
Okay, this is fine, right? Okay. Others also, I hope it's fine. Okay. So I'll move on. Okay. So here's another. So using pumping lemma, show that the following language is non-regular. So 0 to the I, 1 to the J, I is greater than J. This is the question. So again, what you do, you simply assume that let L be regular. We'll assume it's regular. Now what do you do? Since it's a regular, by pumping lemma, and so by pumping lemma there exists P, and any string S in, okay, S is in L, and the length of S is at least P, and S can be written as XYZ, and condition 1, 2, 3. This is the pumping lemma, right? Now, what is a string? 0 to the I, 1 to the J. Okay. Now we want to show pumping lemma for this. So, so P is the pumping length given found by the lemma. The lemma gives certain, it guarantees a certain P. Let's say it's the pumping length. So now look at the most logical thing to do would be take I is greater than J, right? So take something like 0 to the P plus 1 and 1 to the P. Say this is the string S. We can take any qualifying string. It can even be 0 to the 2P, 1 to the P, anything as long as the length of the total string is more than P. Because if it's less than P, pumping lemma does not guarantee anything, right? It needs to be more than P. Okay. So now let's observe. Then it says that you can split x, y, z into so and so and so on. But xy, which is equal to xyz. But xy is at least, at most p. So which means that y only consists of zeros, right? Y is somewhere here only, and say we try to do something like the similar, like the previous one. So let's say y is nothing but 0 to the k, and we pump y. So x, y, y, z will now become 0 to the p plus 1 plus k 1 to the p. Is it in the language still, or is it outside the language, this string? So what is my language? This is my language. Okay. 0 to the I, 1 to the j, I is greater than j. There are more zeros than ones. There are more zeros than 1. So is this string in the language? Or is it outside the language? If it's outside the language, we are done. The language given to us is L equals 0 to the I, 1 to the j, where I is greater than j. Or in other words, there are more zeros than 1. Clearly, there are p plus 1 plus k zeros and there are p ones. So here number of zeros is already greater than number of ones. Again greater than number of ones. So this is still in the language. Okay. Now if I do x, y, I did square. Now let's say I do x, y cube z, which is nothing but 0, p plus 1, which is what I had in the beginning. I pumped y 2 times and y is 0 to the k. If I do it 2 times, then it will be 0 to the 2k, which is plus 2k 1 to the p. And this is still in the language. And no matter how many times I pump y, okay, it'll still be in the language. No matter how many times I'll do it. Okay. No matter how many times I do it, it will still be in the language. So I cannot obtain a string by pumping which is outside the language, which means I cannot prove that it's non-regular that way, right? But there is one small fact to remember here. Okay, why I did this example is not only can you pump up, okay, you can even do something called pump down. Because remember that pumping lemma says for all I greater than equal to 0. So I can pump it 0 times also. What does it mean to do y to the power 0? What does it mean? If y is, let's say, ABC, okay, or a, if y is ABC, then what is y to the power 0? It is nothing but the empty string, right? Y to the power 0 is empty string. So what I do is x y to the power 0, I pump 0 number of times, that is allowed, which will give me 0 p plus 1, and remember I have removed the original y from there, which was of length k, minus k 1 to the p. Now k is non-zero, and clearly number of 0 is either equal to or less than number of ones. So p plus 1 minus k is less than equal to p, because k is greater than 0. Then we have that this string x y to the 0 is not in the language. I wanted to show that you can actually pump down, but please let me know if you didn't get it. Is this clear? Please let me know, because this side of automata theory is slightly more challenging. So, is it clear? Akshay, Abdul, Suresh? Yeah, Suresh?
Yes, sir. We have to do some required practice, sir.
Yeah, what?
We have required some practice by own self.
Oh, okay. Yeah, sure.
Concept is understandable, but we need some practice.
Oh, you need some practice. Yeah, that's good. Okay. Yeah, Akshay, you were saying something?
Yes, sir, I understood.
Oh, okay, good. Uh, yeah. So, but once you see few examples, then you'll kind of get the hang of it about how to go about it. Okay. So, again, another question. So, are the following languages regular? Okay. So, the first languages as follows. They are very similar. First thing you observe is they are very similar. Okay. W such that W has equal number of zeros and ones, and W such that W has equal number of 0, 1 and 1, 0. So, okay, before we do pumping lemma or prove non-regularity or regularity, do you guys have any guesses? Are both of them non-regular, or are both of them regular, or any one of them is not regular? Any guesses? They look very similar.
Sir, first A is non-regular.
A is non-regular. Okay. Okay. Second one?
Second one, not sure, sir.
Okay. Yeah.
Because this is the A part is like example 0 power n, 1 power n, right?
Yeah. It's slightly different. It's equal number of zeros and ones, means the number of zeros is equal to number of ones. So it does not follow. Yeah.
0 to power n, 1 to power n, where n is greater than or equal to 0.
0, okay, wait. 0 power n, 1 power n is greater than or equal to 0. You mean this is the language, right?
Yes.
But I'm saying that even something like 0 power n, 1 power n, 0 power n, 1 power n would qualify for this language and not in this language. Because the number of zeros are 2n, number of ones are 2n. They are equal.
Yes.
So they need not follow this sequence. They are similar in the flavor, I agree, but it need not be all zeros followed by all ones. It's the number of zeros followed by number of ones.
Okay. Right.
It's the number of zeros compared to number of ones. For example, 0, 1, 0, 1, 0, 1, 0, 1. This is also valid because number of zeros is equal to number of 1. But it's not, this string is not in this language.
Yes.
Yeah, right. And but yeah, the intuition, I get your intuition, because it almost seems like if you can achieve this, then you can solve 0 power n, 1 power n also quite simply.
Yes.
Right. Yeah. You are right to think that way. And I'll give you another intuition also, which is that any sort of counting that happens is difficult for a DFA to implement. So here you are counting the number of zeros and the number of ones. Since DFAs have very limited memory,
right, sir.
It's difficult. But that is true for around 80-90% of the cases. At face value, you can say, okay, this language needs some kind of counting. It cannot be done by a DFA.
Exactly.
Right. But the remaining 10% of the cases, okay, that intuition will not help, because this language is not regular. This language is regular. Because it seems that, like, even in the B language, in part B, equal number of 0 and 1 0. Some kind of counting is happening, right?
Sure, sure.
You're counting the number of 0 1 and you're counting the number of 1 0. There is a counting happening, but still it is regular. So sometimes, what I mean to say is, sometimes this intuition may be it may lead you to a wrong conclusion. So that is why you need, pumping lemma or Myhill Nerode or some kind of theorems to tell you for sure that okay, this is not regular or this is regular. Okay. Anyway, that was the comment I had. Okay, I'll show you why this is regular. We can make a DFA for this. Okay. But yeah, your first the what you said, Suresh, in the beginning, that this is regular is correct. This is not regular is correct. So, and we can prove it using pumping lemma. Okay. So W such that W has equal number of zeros and ones. So how do you come up with such a string, okay, that you want to split and then pump and then show that after pumping it's not in the language? Okay. And I won't, now that I've shown the previous examples, I won't tell you, okay, assume L is regular and so on. This is understood, okay. Assume L is regular, it can be partitioned into X, Y, Z and so on, the three conditions and so on. The problem is in finding the particular S that achieves it. The creativity is there, finding the particular string that you pump. So always remember that the string should belong to the language. So it should be something like 0 to the n, 1 to the n, like you said, okay. It has equal number of zeros and equal number of ones. And since it should be compared with p, the length should be comparable with p, and since the length should be at least p, in other words, I do 0 to the p, 1 to the p. Let's say this is my string. And yeah, and that is it. That is the intuition. You always want to take a candidate from the language and fit the p accordingly. Okay. Now this is my string. Now what do? I again observe the length of xy is at most p. So y lies somewhere here. So let y be consisting of all zeros. Let in fact it be 0 to the k. Then x, y to the z, x, y, let me pump it one more time. X, y, y, z equals 0 to the p plus k, because I pumped k zeros in it, and then followed by 1 to the p. So number of zeros does not equal number of ones. Does not equal number of ones, which means that x, y, y, z is not in the language. So this does not follow pumping lemma. So L is not regular. Okay. So in fact this was simpler than the previous ones. So you can try with various languages and check whether you can determine whether it's non-regular using pumping lemma. Okay. And W says that W has an equal number of 0 and 1. 0, 1 and 1, 0. I think I'll leave this as an exercise. Okay. And maybe the next week we can, maybe I can show you how to do it. But try to go across different strings, and it's not very difficult to come up with a TFA for this exercise. Okay. Come up with a DFA for B, the language in B. Okay. And a tip I give you is observe strings where there are equal number of 0, 1 and equal number of 1, 0. Okay. and then try to construct a DFA. I hope that's okay. But if you want also, okay, right now you can tell me if you want me to show the DFA for it. Okay, but you can try it yourself offline. That's what I'm saying. Okay, now that is over. Okay, so before moving on to the next step, I want to brush up a bit on regular languages. Okay, so that you know the next theorem that I talk about, it is clear why the theorem holds. Okay, so here's my question. Let's say L1, L2, L3 and so on be an infinite family of regular languages. This sequence is infinite. We already know that there could be infinite regular languages because there are infinite DFAs. Okay, so there are infinite sequence of regular languages. Okay, so this is regular, L3 is regular, L4 is regular, and so on and until infinity. Is it true that if I take a union over it, okay, that is if I do L1 union, L2 union, L3 union, L4 and so on, the resulting language is also regular?
Yes, sir, it should be regular.
Okay, why?
Because it is the closure property of regular language. The union of two regular languages gives a regular language.
Okay, okay. And others, Abdul and Akshay, do you have any opinion? Would this be regular?
I think it is regular.
Okay. Okay. Okay, so I'll give you an example. Okay. Take an infinite non-regular language. Okay. So, for example, 0 to the, yeah, Suresh, your language, 0 to the n, 1 to the n, such that n is at least 0. Now, what is this? This is nothing but, okay, let's do, n is greater than 0, let's do that. Now, this is 0, 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, and so on. Right. Now from this, let me construct a language 0, 1. From this, I construct a language 0, 0, 1, 1. From this, I have a language 0, 0, 0, 1, 1, 1. Let's say this is our sets of languages I come up with. Okay. And this is L1, this is L2, this is L3, this is L4, and so on. So now I ask you the question, is L1 regular? Forget about the remaining things. Is L1 equals 0 and regular? L1 equals 0, 1. It has only one string, 0, 1. Is this regular? Or I can ask you differently, is there a DFA for this language? Can I make a DFA which accepts only 0, 1? The string 0 followed by 1.
It can be, sir.
Yeah, right. Exactly. I do a 0, then I do a 1. In fact,
Yes.
you might, yeah, right, Suresh?
Yes, yes, sir.
So, and you might have seen in the lectures that any finite language is regular. If you don't, it's a nice tool in your toolbox. Any finite, if any language has finite number of elements, it is regular. You can always make a DFA for it. But even if you don't know that, it's okay. You know that you can always make a DFA accepting 0. You can always make a DFA accepting 0, 0, 1, 1. Right? And so L1, L2, L3, L4, and so on are regular. Because you can always make a DFA for each of them. Right. But what do you see? The original language L, this is clearly non-regular. We've recently proved using pumping lemma that 0 to the n, 1 to the n is not regular. And after, this L1, L2, L3, L4, and when we union them, we are getting L, which is non-regular. Right? But clearly this is a counter example to the question 4, right? So what does it mean? It means that it is not true that the union of infinitely many regular languages is also regular. Because this is clearly a counter example. Okay, if you take L1 equals 0, 1, L2 equals 0, 0, 1, 1, and L3 equals 0, 0, and so on. This infinite sequence of, yeah, Suresh.
Sir, it means 0 to power n, 1 raised to power n, where such that n is greater than 0, which generate the string 0, 1, 0, 0, 1, 1, 0, 0, 0, 1. It may be regular.
What is regular?
For which we can build a finite automaton.
Yeah. I mean, by individually they are regular. No, this is regular. This is regular. This is regular, and so on. Right? You mean that, Suresh?
Yes, yes, sir. Yes, yes.
Yeah, individually they are regular. Exactly. That is what I'm trying to say. Individually.
Why we,
yeah.
Then why we said that 0 and 1 n is not non-regular?
Oh, see, individually these languages are regular. But when you put them all together, then this is not regular.
Okay. It means it depends on the condition of n.
Exactly. This is a very simple language. This language has only one string. This language has multiple strings.
Okay.
If a language has only one string or finite number string, we can always construct a DFA for it, and therefore that language is regular.
So if I restrict the condition like n is equals to 3.
Oh, n is equal to 3. You do this.
Yes, then it will be regular?
Then it will be regular. Good.
Okay.
Because I am just looking at 0, 0, 0, 1, 1, 1. Or if you mean, less than equal to 3, if you mean less than equal to 3, still I'll have finitely many. Right. I'll have 0, 1, 0, 0, 1, 1, and 0, 0, 0, 0, 0, 0, 0, 1, 1, 1.
Okay.
But the fact that n is unbounded here, oh no. The fact that n is unbounded here, n is not finite here. Okay. And the fact that the size of the set is infinite, okay, is playing a role here that it is not regular. You cannot have a DFA for this language. And we saw it using pumping lemma very recently. We just proved it. Okay, we didn't prove it actually. Sorry. But the proof is very similar to A. It's exactly similar to part A of 3. Equal number of zeros and equal number of...
Yes, sir.
Yeah, okay. Yeah, sorry, I assumed that in here that it's not regular. I'm sorry. But it is true that this language is not regular. Okay. But what I'm trying to say is here is we see a clear counter example to this claim, right? I just give you an infinite list of regular languages whose union is not regular. So therefore, it is not always true. Okay, but yeah.
Sir, one suggestion from my side.
Yeah.
Sir, actually, I enrolled in this subject and I am doing the assignment, right?
Yeah.
So, 2 assignment has already been checked.
Right.
And we find some wrong answers.
Right.
So, my suggestion is that, sir, can you explain these questions, means assignment questions, in this session?
Assignment question. Oh, in this session.
Yes, sir.
Okay, I'll do it at the end.
Because that will be fruitful for us, because these things we already learned or we already heard in the lecture.
Yeah, sure. That makes sense, Suresh.
Sir, so it would be good that if you take the checked assignment and if you go through that the questions of the assignment, then it will be fruitful for us.
Yeah, sure. I'll do that. Thanks for the suggestion. But at the same time, I also need to cover the questions belonging to this week itself, because that way you will have some help in solving the questions given in the assignment for this week. So, but thank you, Suresh. Then what I'll do is I'll do a bit of both from now. Okay.
So, sir, in assignment 1 and 2 has been checked, right? So you can take both assignment in the next session.
Sure. Yeah, sure. Or if you have particular questions, we can do it at the end of the session also.
No, sir. All questions are good. All questions are good, sir. So we have required the explanation of that question. So if you will take all questions, if that will be easy, it will take 1 or 2 minutes. If maybe hard, then it will take 2 to 4 minutes.
Yeah. In about an hour, I think the entire assignment will be done. Yeah.
So please take this as consideration, sir.
Yeah, sure. Thanks for the session. Yeah.
Okay. Thank you, sir.
Okay. Okay. Yeah. Okay. So yeah, today's session at the end, maybe we can do a few questions from the assignment. Okay. Maybe at the end. But okay, I'll complete the remaining. Okay. So yeah. Okay. Now, why did I ask this question here? Okay, is because DFAs. Okay, is because Suresh, you told me that this is regular because of the closure property, right? Regular languages are closed under union.
Yes.
But why did it not work here? Because you are taking
due to the infinite nature.
Due to the infinite nature. But why is the infinite nature causing a problem? Because
it will not. Because sir, it will not follow the property of pumping lemma. If you will take the infinite language, somewhere it will get the false condition of the pumping lemma.
Okay. But we are not using pumping lemma yet, no, here. And we just said if I have infinite number of regular languages, the union will not be regular. Okay, I'll tell you why. Because how did we prove that union of regular languages was also regular? We did it by something called subset construction, right? What we did was, right, we took all the states of the first DFA and the second DFA. We did a cross product between them, and then we got a DFA which is a union of both. What happened here? The number of states increased. Okay, fine. Then let's say to a language L3, I do the subset construction once again. Then I get another DFA, L1 union L2 union L3, and then I do subset construction again with L4, and so on. But I do this infinite number of times. What will be the size of my final DFA? The size of the DFA, since I did it infinite number of times, the resulting DFA will be of infinite size. This cannot exist. Why? Because DFA, the definition is the DFA should always be of finite size. The description of DFA is always finite. Number of states is finite, number of symbols is finite. So this is why it was misleading to say that because of closure properties, I do it infinite number of times, then I obtain a DFA, correct DFA. But notice that every time you do the union using the closure property, you get a bigger DFA, bigger and bigger DFA, until if you do it infinitely, you get an infinite size DFA, which is not possible. So that was the problem. That was why it was not working. Okay. Yeah. Now there's a reason why I did this. Okay. It's because I want to solve a few problems on Myhill Nerode theorem. Okay. So now what is now pumping lemma only talks about one direction. Okay, is one direction. So a disadvantage is it cannot identify every non-regular language. But Myhill Nerode theorem is slightly stronger. It's much stronger actually. It says if a language is regular, then definitely some conditions are satisfied. And if a language is not regular, then definitely other conditions are satisfied. Some other conditions are satisfied. So this is very strong. Right?
Yes, sir.
So this is very strong. This is a litmus test. Okay. If your language you testing is definitely non-regular, then it is definitely going to, we are definitely going to identify. But this is not the case with pumping lemma. There are ways to fool the pumping lemma. Okay. So I think these things were covered in the lectures. So I'll just say two strings x and y are distinguishable by a language L if there is a string. If there is a string in sigma star, any string, such that when I concatenate it with x, when I do xz, then it is in the language. If I do x and yz, then it is no more in the language. Okay. Then these two are distinguishable. Or similarly, yz is in the language and xz is not in the language. But both it cannot be. Okay. For example, x is 0, 1, 1 and y is 1, 0, 0. And L is all languages which has even number of zeros. Then if I take z as 0 and concatenate at the end, then even number of zeros, then it's in the language, and odd number of zeros, when I put another 0 here, then it's no more in the language. So it's not in the language. Then x and y are distinguishable. If it is not the case, if no matter whatever z I put, okay, they will always belong to the same language, then they are what are called indistinguishable strings. And they are said to form an equivalence class. What it means is we are supposed to say x is equivalent to y for L. Language L cannot differentiate between x and y. Now, theorem, here the simplified version of the Myhill Nerode theorem. A language L is regular if and only if the equivalence, there are finite number of equivalence classes in this particular relation. Okay, but we want to prove non-regularity. This is saying if it is regular, then something, if and only if something. We want to say if it is not regular, then what? Then since it is an if and only if, we can complement both sides we can say if L is non-regular, then there are infinite number of equivalence classes. Okay, but okay, simply how do you do it? How do you prove non-regularity? What we want to do is we want to come up with an infinite set, okay, S, and show that any two strings are distinguishable, which means I need to find a Z such that in the language, so that when I do XZ, it is in the language, and when I do YZ, it is not in the language. Since X and Y are distinguishable, okay, they belong to different equivalence classes. Okay, now since S is infinite, okay, the set I took was infinite, the number of equivalence classes will be infinite. Since they are in different equivalence classes, and since S is infinite, number of equivalence classes will be infinite, and by Myhill Nerode theorem, if there are infinite number of equivalence classes, then it is non-regular. But even if this procedure was not clear, I'll show you via an example. Okay, it's very simple actually. It might look very daunting. So here are some of the languages. So here is the language again, the same language we saw before. We could prove this using topping lemma also. But here we are now saying that W such that W is of the form, okay, 0 to the n, okay, 0 to the n, 1 to the n, and let's say n is greater than equal to 0. We want to prove it's not regular. So what do you want to do is you want to come up with an infinite set. Okay, so what is an infinite set? I'll give you an example. For example, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and so on. Okay, now choose some 0 to the k which belongs to S. Now we want to choose the Z that we want to concatenate. Okay, we want to choose Z such that 0 to the k Z, okay, this is our X, okay, and some Y which is 0 to the L is also in S, and L is of different, not equal to k. Okay, we are choosing one element here and let's say one element here. One is X, one is Y. So we want to choose 0 such that 0 to the k Z is in L, and 0 to the small l Z is not in L. So what I'll do is I'll choose Z equals 1 to the k, then I observe, oh, 0 to the k, 1 to the k is in L, but 0 to the k, 0 to the L, 1 to the k is not in L. Why? Because k is not equal to L. As soon as you observe this, okay, you got a Z such that 1 is in L. You see that these are therefore distinguishable. Now since these are distinguishable, there are infinite equivalence classes, and therefore by Myhill Nerode theorem, L is non-regular. Okay, this intermediate step you don't really need, okay, because this is a part of Myhill Nerode theorem. But the creativity here is coming up with a set S. Okay, I'll do another one. Okay, B, L equals WW such that W is in 0, 1. So something like 0, 1, 0, 1, 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 0, something like that. I want to come up, okay, I want to come up with a set such that I can distinguish two strings. So L equals WW. Right. Now I want to come up with an infinite set such that if I take an x in S, y in S, two not being equal, both of them not being equal, I want to show that xz is in L, yz is not in L. You want to do something similar to before. What I'll simply do is I'll do 0 1 0 0 1 0 0 0. There are other ways to achieve this. This is just one way. Okay. And let x be 0 to the k 1, and what is y? 0 to the L1. Okay, this is y, and k is not equal to L, and you can see that both of them are members of S. Okay, then what do I have? xz. Okay, and z, what I'll do is I'll choose it identical to, because I want it to be in the language, and since it's a repetition of ww, I'll do z equals 0 to the k 1. Next, what I do, xz equals 0 to the k1, 0 to the k1, which is of the form ww, therefore it is in L. But if I do yz 0 to the k1, 0 to the L1, okay, 0 to the k1, 0 to the L1, and since k is not equal to L, this is w and this is not equal to w, this part, and this is not in the language, and therefore it is not, therefore you cannot, therefore by Myhill Nerode theorem, this is not regular. Okay, so okay, so the creativity is coming up with the set S here. Okay, and can we do anything else? Yeah, okay, I would like you guys to try D. Okay, try to possibly come up with set S, or you can try it right now. I'll give you some time. Try to do D. Okay, W such that W is not a palindrome. How do you use Myhill Nerode to achieve this? Come up with an infinite set, but there is a slight okay, one thing I'll tell you right away. Okay, before directly attempting this, go for the complement. Don't go for W is not a palindrome, go for W is a palindrome, because we know that if it was supposed to be regular, then complement is also regular. Okay, W such that W is a palindrome. Any ideas? Okay, here's how. Choose an infinite set. See, at the end, what I want is I want to append. Okay, I want to put a z in the end such that it is a palindrome in one, it is not a palindrome in the other. Okay. So, if I, let's say, if I take this sequence, this will not work. I'll tell you why this will not work. Okay. 2 0. I want to put another. I want to put another item here so that it becomes a palindrome. What is palindrome? Sorry, palindrome means the reverse as well as the language itself is same. For example, apple is not a palindrome because APPLE is not equal to ELPPA, but something like race car is a palindrome. Okay. If you write race car opposite, it will still be race car. So what do if I add a 0 to it, it becomes a palindrome. But even to 0 0 0, if I add a 0 to it, it still becomes a palindrome. So Myhill Nerode theorem is not contradicted. And so this sequence cannot be worked with. So what if I put 0 1 0 0 1 0 0 0 1 and so on? Oh, okay. Then if I put, if I take 0 1 and then I add a 0 at the end, and if I take a 0 0 1 and I add a 0 at the end, this is not a palindrome, this is a palindrome. So that's it. I've figured it out. All I want to do is I take x equals to some 0 to the k 1, which is in the set, and y equals 0 to the l 1, which is also in the set. What do? I set z equals 0 to the k. Then okay, xz equals 0 to the k 1, 0 to the k, which is in the language. This is a palindrome. Notice that this is a palindrome. If I write it in the opposite direction, it will still be 0 to the k 1, 0 to the k. But if I do yz, it will become 0 to the l 1, 0 to the k, which is not in the. Note that here I am talking about L not equal to K. So this is not a palindrome. So the questions in this side are a bit challenging. Okay, I get it, but if you observe the patterns, okay, then it might be easier to come up with such an S. Okay. So the remaining questions, which is C and E, okay, I leave it to you guys. Okay, so C and E, try it. If you cannot do it, then let me know in the next session. Okay. Okay. So now, okay, now the difficult parts are done. So now we come back to very introductory parts. So I'll do a few questions on context-free grammars, and then we'll call it a day. Or I can even, like Suresh said, I can even solve a few assignment questions. Okay. So here's the question. So we looked at regular languages, and we said that there are actually languages which are non-regular, which are more powerful. Okay, not powerful, they are bigger, I mean more harder, more difficult. But can we characterize them also? Can we say that, okay, out of the non-regular languages, there are some specific type of languages. Those are what are called CFLs. Okay, this is one type. Okay, CFL is a type of non-regular language, and they are slightly more powerful, not powerful actually, more difficult to recognize. What I mean by difficult. So they need a better machine. A DFA, a deterministic finite automata, or an NFA cannot recognize it. They are more difficult. And one application is they are used in compilers a lot. Okay. And programming languages, okay, are an example of context-free languages. And but in this week we are not talking about CFL, we are talking about CFGs, okay, the lectures. So what is a CFG? A grammar, okay, which is of this form. It consists of variables, terminals, start state, a start variable, and a production rule. So what are variables here? Okay, for example, this is what is called a production rule. You might have seen it in the lectures. And what are variables here? S, A, B. And what are the terminals? A, B. Okay, terminals don't have further production. You cannot do something like A gives something. Okay, they cannot produce anything. They are in they can be called constants also. It's like variables and constants. Okay. Now, a grammar helps you describe a language. Okay. Now, what is the kind of languages it's describing? So here I'll show you how. Okay, so S generates ASB. I'll write it in this form. S generates ASB. Now what does A generate? A. Now what does S generate? Again, A, S, B and B. Okay, it's not completely, and let's say epsilon. So what is this symbol? This is an OR. Okay, so which means is S can choose whether to generate ASB or generate epsilon. So let's say S decided to generate ASB again. Now A can only generate A and B can only generate B. Now S can again decide whether it can generate ASB or not. So let's say it again decides to generate ASB. Okay. Now A generates only A and B generates only B. Now let's say S decides to generate epsilon. Now what I do is, this forms a tree. This is called a parse tree. Okay, and if I look at all the leaves from left to right in the tree, leaves meaning the node has no out degree, no arrow going outside. Okay, so what do? From left to right, I look at the leaves. A, then A, then A, then epsilon, then B, B, B. So A, epsilon, B, B, B. And so what did it generate? It generated A, epsilon, which I'm not writing, B, B, B. What if I had cut off epsilon here? Then it would have generated A, epsilon, B, B. Right? What if S had generated epsilon here? Then this production would have ended and I would have generated A, B, B. So I can generate strings that look like epsilon, A, B, A, B, B, A, B, 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 and so on, using this grammar, which means what is the language? A to the n, B to the n, such that n is greater than or equal to 0. Okay. Now this is a quick recap. Now let's look at the questions. So the question says, check whether the strings AABB, BBB, AAA and BB are generated by the following grammar, where S is the start variable and alphabet is sigma AB. So make the parse trees for it. So for the first one, check whether AABBB can be generated. make a parse tree that I just showed just now. Can you make a parse tree that generates this? So can you try once?
Yes, sir. Just a minute.
Yeah. Yeah.
Sir, nothing can be generated.
Nothing can be generated, meaning? Oh, all three. None of the three.
Yes.
Oh,
Yes.
okay. I'll give some more time to the others. Abdul and Akshay. So, Suresh, what is the language of this grammar? What kind of strings does it generate? Any idea?
Trying, sir. Just a minute.
Yeah.
Sir, like single A, double A, triple A.
So it's not generating any B. Oh, sorry. Sorry, Suresh, I made a huge mistake.
Capital B is not terminating
Yeah,
anyway.
capital B is not really there. Yeah, now please try.
No, just a minute. Sir, first will be generated
Okay.
and double B will also generated.
Double B will also be generated. Okay. But the middle one will
Let,
not be generated.
let me
PPB.
check, sir.
Yeah.
Let me check, sir.
Okay.
No, this one will not generate. Triple B, triple A will not generate.
Okay. Let's see. Um, yeah. Here's the first one. AABBB. Let's try to generate. Okay. So S generates AB. There is no choice here. S needs to generate AB. and we need an A in the beginning. So A can generate, we can do either an A or we can do an A, right? There is a choice. But if I only do an A, then B will only generate B's, and then I don't have a choice. I mean, then I can only generate one A, but we need two A's. If you look at the question, we need two A's. So we'll do AA and BB here, and from here I can do AA or I can do only A. But if I do an AA, I need to do an A at least, or an AA, and so on. It will continue forever. I mean, it will continue, or we will have more than three A's. That is the point. So we'll have more than two A's. That is the point. So I don't want to generate another capital A. I want to generate a single A. And finally, I have a capital B here, and capital B will generate small b, capital B, and then I don't want to generate B's more than once now. I'll just generate a single B. And now let us look at all the leaves from left to right. A, B, B, B. Right? A, B, B, B. This is the direction you want. Okay. Now I observe that A, B can be generated. Now let's try for the other one. B, A. This is the string. Now S needs to generate A and B. Now look here. A needs to generate at least one A. It can generate more A's using this first rule, but it needs to generate at least one A here. And B needs to generate at least one B. But now we observe that we need B before and A at the end. But since A needs to generate at least one A here, at least one A ends up at the beginning. Needs to happen. But since we are beginning with a B, there is no way that this sparse tree will ever reach a B in the beginning, because we are moving from left to right, and it will see an A in the beginning. So it's not possible. Not possible. Okay. Now let's try the final one. Let's try C. C is BB. But again, you see that A will generate at least one A. Will be generated. But the string we need to generate is BB. But need BB. So obviously, since we need at least, any string we generate will have at least one A anyway. There is no way to generate BB because BB does not have any A. So is that clear? Suresh, you are correct about the first two, but the third one cannot be generated.
Actually, sir, I solved with the with the production rule A produce BB. That's why I was.
Oh, okay, sorry. Okay, yeah, okay.
Yes.
Okay, the previous one. Yeah, sorry for that.
I took A produce BB. That's why.
Okay. Yeah. That was completely my mistake. Okay.
Yes.
Okay. So give CFGs that generate the following languages. So I'll do the first one. The remaining I'll try. I'll let you guys try. Okay. The first one is L is equal to all the strings that contain at least 3 ones. Okay. And sigma is 0, 1. So, how do you come up with a grammar for this? Contains at least 3 ones, right? So let's do this. What does the strings look like? Strings look like some zeros and maybe one in between, and then zeros and maybe one in between, and zeros, and then one in between, and then maybe zeros. And it may be that one and two ones are consecutive, but in that case, this part can be epsilon also, can be empty string also. In other words, this is nothing but 0 star 1 0 star 1 0 star 1 0 star, right? This is a regex regular expression for at least 3 ones. At least 3 ones. So I'll use a similar technique here. S produces zeros followed by ones followed by zeros followed by a single one, or I can even do 1, because you can directly put the terminal, right? Followed by zeros followed by 1. Now what does Z produce? Z produces only zeros. Produces 0 Z or epsilon. So this can be used to do star operation, because what does Z produce? Z produces 0 Z, Z produces 0 Z, and 0 Z, and so on until some epsilon, then it will form 0 star. So that's why I gave this. Okay, so this is a grammar producing the language. Okay, now I give you, try question B. L is all the W such that W has odd length. All the strings that have odd length. Slightly tricky. Okay, I'll explain. the trick is to observe how you can produce strings such that it's always odd. What I mean by that is, take any odd number. Okay. An odd number can always be written as 2 times k plus 1. Odd numbers are very symmetric in that way, such that let's say you have 5 fingers, right? I have 5 fingers out here. This one finger I have, okay, in the middle, it is in the middle, okay, I have odd number of fingers, and I have one finger in the middle. The 2 fingers on either side are always even. Okay. In other words, if I take any odd number, okay, odd number of items, on either side there are always even number of things, because an odd number can be written as 2k plus 1. So that is what I want to emulate. The middle term is always there, and on either side I have even number of. So what I do is as follows. S produces, okay, a term in the A S B, okay, ASB, such that A generates 0 or 1, okay, ASA, let's say. B generates either 0 or 1, and S at the end should also either produce a 0 or 1. I'll explain why this works. So let's say you have S here, it generates ASA, okay, and S produces ASA, and this produces ASA, and this produces ASA. Now A must produce either 0 or 1. Oh, sorry, B is not there. A must produce either 0 or 1. Here let's say it produced 0, here it produced 1. Okay, fine. Here it produced a 0, here it produced a 1. Okay, here it produced a 1, here it produced a 1, let's say. No problem. Okay. Oh, okay, sorry. I made a mistake in the observation. The sum of left and right, okay, is even. Really sorry. The sum of left side and the right side is always even. So here you observe that S at the end needs to produce either 0 or 1. It will produce, if it produces a 0, then what do you have? On either side, I have 0, 1, 0, 0, 1. On this side, I have 1, 1, 1. But what is the number here? I have 3 symbols here. I have 3 symbols here. It will always be the case that I produce 3 symbols here, 3 symbols here. If I produce 4 symbols here, I always produce 4 symbols here. Because at every level of the tree, I'm always producing 1 symbol on either side. So therefore, if I produce 4 symbols here, I produce 4 symbols here, and so on. And when I add 4 plus 4, it will always give an even number. 3 plus 3 will always give an even number. In the middle, I give a 0 or a 1. I give a single symbol, and then this plus this even plus a single symbol will always give odd because of this 2k plus 1 rule. Okay. So, for example, if I want to generate 0, 1, 1, 0, 1, 1, 0, 0, 1, 0, 1. So this is an odd length, right? What is the length of this? 5. So what I do is For this I do S. S generates what? A as A. And this gives 0, this gives 1. And S generates A as A. And both of this gives 0. And this middle S generates 1. So 0, 0, 1, 0, 1. So this is my grammar for this. Okay, so final question here. L equals empty. Any idea how to do this? L equals empty. In other words, L does not generate any string. The grammar does not generate any string. Any idea? Think of the parse tree. Like, what does the parse tree look like? And mind you, I do not mean it generates the empty string. Okay, the language is empty, the string is not. So this is not the same as okay. So here is how. If I do S generates some A and A generates B and so on. If I look at the parse tree, it will generate an A and then it will generate an B. If I do A, B and then B gives some epsilon, then S generates B here and then epsilon and so on. This kind of grammar which has terminals will never work out, because a leaf, as soon as I obtain a terminal, will always lead to a leaf. That's why it's called a terminal. Okay, it will always lead to a leaf, and if I get a leaf, I get a string, and if I get a string, then the language will not be. Therefore, need a grammar without terminals.
It's not possible, no, sir.
Why?
Because a grammar can be context-free grammar if contains VTPS, variable terminal production symbol or start symbol.
Exactly. Variable terminal start state production rules.
And production. Yes.
What is this? This is a set, right? What is T defined as? T is a subset of sigma, the alphabet. It can be A, B, 0, 1, whatever.
But not empty, but not phi, no?
But not?
Phi means empty string.
It can be, right? Since it's just a subset, it's
okay.
Right.
So for phi means empty string, we can write context-free grammar.
For empty string, you can write context-free grammar, but for the empty language also you can write. Remember, this is an empty string. This you can easily do. You just do S generates epsilon.
Yes.
But what I'm asking you is phi, which is the empty language.
But for empty language, we can't create any CFG.
Why can you not? I just wrote here that you need a grammar without terminals.
Yes, sir, because it's required one terminal symbol, right?
No, terminal is a subset of sigma, so terminal can be
Yes,
empty. It need
yes,
not
yes.
contain any symbol.
Right.
We are not violating the definition. I'm glad you
Okay.
brought it up. Yeah, because we are not violating the definition of G.
Yes, yes, yes.
As long as I give at least one production rule, at least one variable, I'm fine. So, so now what do I do? I just do S generates S. This is my production rule. What will the derivation tree look like? Oh, okay, S generates S, S generates S, S generates S, and so on. It will be an infinite tree, but we never reach a terminal only, and therefore it ends at infinity. In other words,
It is also called ambiguous grammar.
this one is not ambiguous. Ambiguous meaning,
Okay, sorry.
yeah, yeah.
Okay.
Ambiguous meaning the same tree can give different. Oh, sorry. Uh, the same string can have different trees.
It looked like recursive.
Yeah, this is recursive. This is recursive. Yeah, this is an example of infinite recursion.
Yes, and in compiler construction, there is a way to remove the recursive grammar.
Yeah,
We can
yeah,
rewrite this grammar.
recursion is can be removed. That's right.
Recursive, because recursive grammar is not acceptable by the compiler.
That's right. That's right.
Yeah.
That's right. Yeah, and
That's why we use some the technique to remove the
there
recursive.
are techniques. Yeah, right.
Yes.
In compiler design. That's
Right,
right.
sir.
Good. And so this cannot generate any string. Therefore, language generated is empty. Okay. Okay, we are almost okay. So, what are the okay? We'll just quickly look at one part maybe, and the rest you can do it offline. I'll upload this PDF anyway. Okay. So the question is, what are the languages generated by the following CFG production rules? Identify the variables terminals in each grammar. So yeah, tell me what are the variables in this? What are the terminals?
Terminals are small b, null.
Small a, small b, null. Okay.
And
Variables
variables are capital A, capital B, and S also.
and s also. Good. So can you tell what is the language generated by this grammar?
A, B, B, C.
Okay, that is one string. But what is the general language? It can generate a bunch of strings, right?
Okay.
That is one string. A, B, B, C. Try generating more strings. What is the general pattern you see? That's what I'm asking.
another is small मतलब BBCC.
BBCC. Okay. Because A side generated epsilon, right?
Yes.
Okay. Let's further generalize it. Okay, I'll show how. So we'll look at the big picture. Okay, S generates A, and this side it generates B. Okay, and here let's not immediately generate epsilon. Let's do another production, A, B, and here also let's do another production, B, 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 and again A, B, B, B. Oh, sorry, here it should be C, right? C, A, B, 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 C. Okay, are you seeing the pattern? Now let's say A generated epsilon, stop in A, but let's say B is not happy yet. B still wants to generate. Then B says stop. So what is the language? What is the string generated? String generated is A, B, or let me write A cube, B cube. Then how many B's? 1, 2, 3, 4, 5, 6. 6 B's. And if you count, there are 6 C's. You observe that on A's side, the number of A's will always be equal to the number of B's. And on B's side, the number of B's will always be equal to the number of C's. Number of A's is equal to number of B's. And here, number of B's is equal to number of C's. That's why we got A to the 3, B to the 3, and B to the 6, C to the 6. Okay. And similarly, we can even get A to the 4, B to the 4, B to the 10, C to the 10. In general, what is the language? The language is nothing but A to the M, B to the M, B to the N, C to the N, where M and N is at least 0. Why 0? Because like you said, because if in the beginning if A generated epsilon itself, then M is 0. Okay. So is this clear?
Sir, can we?
Yeah.
Yes, sir. Can we take another production?
Can we take another product? Do another. You mean this example?
Yes.
Okay, sure.
Take. Yes, sir.
Okay, sure. So yeah, here is one production. Okay. S.
No, sir. In question first, A
Yeah.
part.
Yeah.
Take the production S produce AB.
Oh, okay. That way. Okay, sure. S produces AB.
And A produce null.
A produces null.
And B produce small b, capital B, C. Now expand this. Also
Yeah.
expand the
Now
capital B.
null I cannot expand further, right?
No, null. No.
Okay. Yeah. Now
capital
then
B.
I can only expand B. Now let me expand
Yes,
B.
yes.
B gives BBC.
Yes.
Then again B gives BBC. And then I do
Yes.
null. See.
Yes.
So what do I do when parsing it? I get epsilon B cube C cube. And epsilon is nothing but empty.
Yes.
but my claim was it was a to the m, b to the m, b to the n, c to the n. No.
Yes.
So what do? I just say m equals 0. If I do, okay, which is nothing but a to the 0, b to the 0, b to the n, c to the n. And this a to the 0, b to the 0 is nothing but epsilon.
Okay, fine.
Getting it? So look at the bigger picture. That's what I say.
Yes. Try to generate the bigger string.
Yeah. Try to generate a bigger string and try to separate them into blocks. Try to separate the trees into blocks. For example, here's the A block and here's the B block. And A block has a certain pattern, B block has a certain pattern. So the entire block S has a collective pattern. Getting it? Okay.
Yes, sir.
Okay. So okay, it's almost 8 right now. So here is another question on production. I'll let you guys try it on your own. And yeah, here is another question on production. I'll let you guys try it on your own.
We will do it, sir. No issue.
Sure. And here is a simple question which talks about the application on compilers. So you can try it. Okay. So that brings us to the end of the session. So see you next on Tuesday.
Sir, one question from my side.
Yeah.
Sir, please write down.
Yeah. Oh,
sigma.
Sure. One moment. Yeah.
Sigma equal to 0, 1.
Okay.
How many number of regular language we can generate it from it?
Number of regular languages generated. Okay, Suresh, this question, I don't have an idea how to give an absolute count, but I don't think that is possible also. I think, but I can give a bound for it. We can give an upper bound for it. Okay. But I don't think it is possible to tell exactly this many. Oh, okay, yeah. It is not possible to tell exactly how many because it's obviously infinite. So yeah. So let's try to give an upper bound for it. So how we can do it is count number of DFAs. Okay. So what is it? What does a DFA contain? DFA contains sigma.
But it will generate infinite language, right?
Yeah. I mean, sorry, infinite number of languages. That's what you are saying.
Infinite number
definitely.
Of languages. So we can't count it, na?
We cannot count it, but we can show why it's infinite. Yeah, sorry, not an upper bound. It's not exactly an upper bound, but what I meant to say is I can show that it's infinite.
Okay, sir.
How? By showing that the number of DFAs are infinite.
But how many DFA we will create? Because the language is infinite.
Exactly. By showing that number of DFAs are infinite. Okay.
Okay, sir. Okay.
So what's there? Okay, sigma is there, but okay, start the states Q and start state.
No issue. Actually, my request is to please revise or do some exercise from sir assignment. My request is that. Because this is the assignment question, sir. Or such type of questions not possible with the help of these lectures. I am facing this.
Oh, okay. Sure. Yeah. Okay. But okay. I get your request. But yeah, that's what I'm saying. It's infinite.
Okay.
But it's not just infinite. There are different kinds of infinities. It is countably infinite. In set theory, you might have heard of countably infinite, right?
Okay.
Right. So, for example, the set of all real numbers is bigger than the set of all natural numbers. Even though this is infinite, this is infinite. Okay, things like that. Anyway, so yeah, the simple answer is there are infinite number of DFAs I can create. I can always add a new state.
Okay.
Right. And since I can add a new state, always there are infinite number of DFAs, and since DFAs recognize regular languages, there are infinite number of regular languages.
Okay, sir.
Okay. One question I want to add because of this. Okay, I wanted to do it during problem set discussion is how many languages are there? Okay, over sigma star. This is what I want to leave you with. I can tell you the answer also right away, or if you want to try it yourself. What do you want to do? How many languages are there over sigma star? I mean, you may think, you can get time to think about it offline also. I don't mind telling the answer next session.
Sure, sir.
Okay, you want to think about it? I mean, offline.
It may be, sir, infinite.
It is infinite. Good.
Because sigma 0, sigma 1, sigma 2, sigma 3.
Yeah. Yeah, that is there. And but you can get more out of it also. Like what exactly?
We will do the exercise on this question.
Yeah, sure. It's yeah, okay. Okay, yeah, I'll keep your suggestion in mind and do the next session, problem solving session accordingly. Okay,
Because now if you take the assignment questions, now the OR theory will be recapped already.
That's right. Okay, sure.
So I think it would be beneficial for us.
Yeah, makes sense, Suresh. I'll do the assignment questions next time.
Because at present what we are doing already these all things we have learned in the lecture.
Right.
Taught by sir, right? So I think this session should be on the problem specific, and I am not saying that take the question from upcoming assignment. Take the questions from already checked assignment.
Yeah, makes sense. The only reason why we are doing it this way is because we want the current problem session to help you solve the coming assignments. So that is why I am discussing questions on the assignments that you are yet to do, the topics that you are supposed to submit your assignments on, but not the exact questions. So that is the intention behind this. But what you said is also correct. But you understand what I'm saying, right? Yeah. So,
sir, pardon, please. Actually, I have lost my connection.
Oh, okay. What I meant to say is why we are doing it this way is the intention behind it is because we want the problem session, the current problem session, to help you solve the coming assignments.
Sir, but the questions pattern is not in the way that by these lectures we are able to solve this.
Yeah, sure. I mean, it is not exactly, and especially the questions are also not same, and it cannot be too similar also. But that is the main intention. Okay, that is why the sessions are designed in such a way, but I don't mind
I
changing
know,
it.
sir. It's approach. I know.
Yeah, but I don't
Approach
mind
is
changing.
good. I am not saying that it's wrong.
Yeah, no. I
Its
see.
approach is good, sir. We are revising the things.
Right. Yeah.
But my request is that just take the assignment. Like na, in next session we take the session on assignment. Assignment one. There are questions, and questions are one-liner. So it will not take
Definitely.
more time.
Yeah, definitely. So what I'll do is, Suresh, is okay. I'll there are not see it does not take a lot of time to discuss the assignment solutions. Okay. So what I'll do is I'll separate the slot into two halves.
Okay.
Maybe the first half I'll discuss the past assignment solutions, everything. Okay. So
Yes, yes,
let's say
yes.
I take assignment one and I solve it.
Yes.
Okay. I mean, at least I tell you what the answers are. And next,
Sir,
what I
not
do?
all questions. Sir, not need to take the all questions. There are some questions like suppose that in assignment there are 10 questions. So like 6, 7 questions we already done and it's right. But
Okay.
there are 3, 4 questions which wrong in any way or due to some lack of information. So such type of
Okay.
questions you can take.
But the problem there is how do I identify
Just,
how do I
just a
identify
minute, sir.
which questions
I'm
are solved?
sharing my screen.
Yeah.
Just a minute, sir. I'm sharing my
Sure.
screen.
Okay. I'll stop sharing from here.
Yes.
Okay.
As well.
Yeah.
So to look here, sir.
Okay. Okay. So it does not show the reason why your answer is incorrect and so on.
Yes. So if you explain why it's wrong, then we will get some knowledge about it. Like
Okay. Sure.
you can see that the answer is in. That's it.
Hmm. Yeah. Okay. Um, yeah. So okay, I'll try to identify the questions which may be tougher for you guys to solve. And those questions I'll solve in the first half of the session. Okay. If you like
Yes,
you
sir.
said if
Actually,
there are fewer questions, then I can even do like assignment 1 and 2 both in the next session, coming session.
because sir, because now in last turn I have asked you one question,
Hmm.
right?
Yeah.
So like this one.
Right. Yeah.
The number of possible languages. I asked these questions separately with you.
Oh, okay. So there was a mistake there.
Yes, sir, it was wrong. So after the I didn't understand that why it's wrong. So
Oh,
that's why I'm
okay. Yeah.
asking.
Okay, I can I can already see why it's wrong because I had mentioned that time that we are assuming that the DFA
No issue, sir.
does not
No
show dummy
issue.
state. But yeah.
Yeah.
Okay.
Do not take it otherwise.
Yeah.
It's my problem. That's why I asked.
Yeah. But one thing is, but you did not mention that time that these are assignment questions.
Yes,
So
that's
I'm
why
not.
today I told you. That's why I today told you that there are some questions.
Yeah. No. What I mean to say is I'm not supposed to reveal the assignment question. I mean, assignment answers,
No issue, sir.
which are coming up and coming.
I will not ask the question from upcoming assignment. I
Yeah.
am just saying you that just take the past assignment which has been checked.
Yeah. I get it. I'm talking about this particular assignment that you have.
Yes.
Okay.
Okay, sir.
Okay. Yeah. But yeah, this also I'll explain why this happened. Okay. At least
Yes.
in
No issue,
question
sir.
4, I'll explain what happened. Question 5 must be an error in my judgment. Yeah. question 5 probably made a miscalculation, but question 4, yeah, I'll explain next time why it's 2.
Sure.
Okay.
Yes, sure.
But yeah, okay. So I'll do that from next time. I'll allocate 2 different slots, and I'll discuss the previous assignment in the first slot.
Yes. Only those assignment which has been checked, we will discuss it.
Yeah, exactly. And in the second slot, I'll do the current week's matter.
Sure.
Okay, I'll do that. Okay, that was a good suggestion from your side. Okay. Okay, so I think we've come to the end of the session. Anything else?
No, sir. Thank you so much.
Okay, then we'll meet. Week 4 is on Tuesday again, 6 p.m. Week 5 will be change of slot. Okay, I'll let you guys know when the changes. Okay, week 5 will be on a different slot.
So you will be available in week 5?
I will be available in week 5, but it won't be on Tuesday. It will be on Saturday. I'll announce it on week 4. Okay, and you guys will also get a reminder email. You won't get it on Tuesday. You will get it on Saturday instead of Tuesday. But the coming week, week 4, okay, will be on Tuesday.
Fine, sir.
Okay, so to repeat, the next week session that is coming will definitely be on Tuesday.
Okay.
I'm talking about the week after that.
Okay, sir.
Okay, Tuesday 6 p.m. I'll prepare accordingly. Okay then, see you guys that time.
Okay, thank you, sir.
Okay, thank you guys. Okay, thank you, Suresh.
Bye, sir. Thanks, sir.
Okay, thank you, Akshay. Thank you. Good night.
Good night, sir.